Okay. Yeah, so first of all, thank you, Jens, and the rest of the Algebra team to invite me to give this talk. Getting here, I got some flashbacks from, let's say, a good 7 years ago when I also had to come here and make sure I was here in time for the start of the course, because I only got here in time like 10 minutes before the talk. So, all right. Yes, today I will talk about free and amalgamated products in group rings. And my idea is to basically give you an idea on how these two different topics, so free and amalgamated products, they are, let's say, a subset of geometric group theory, and group rings, which is more of a representation theory object, how they are related. Now we'll do this by, of course, first giving some definitions, right? And then giving you some motivation on the kind of problems that we're thinking about in group rings, coming from a couple of conjectures. Okay, and once I have this, once I have introduced these conjectures, then I will tell you how I believe these free and amalgamated products can actually help for them. And yeah, I think that's about a good idea of what I will talk about. Okay, so first of all, let's start with the basics. Chapter 0, intro, and notation. So first of all, always when I write G, I will mean a finite group. And if I want to talk about arbitrary groups, so not necessarily finite, I will write it as a calligraphical capital letter G. This is like an arbitrary group. Okay, and then R, I will always denote a ring. Generally, we'll assume with units, and special kind of rings, namely fields, will denote by F. Okay, so for me, fields are always commutative. Okay, once you have these two objects, so groups and rings, you can create a new kind of ring, and the new ring is a group ring, and we'll denote this by RG. Okay, for a ring, you need two things. First, you need an additive structure and you need a multiplicative structure. Okay, so the definition as additive structure is basically a free R module on the group G. Okay, so basically what this means is that you take abstract linear combinations of group elements and you allow, so a combination like this, and AG is an element of your ring. And then I think it's quite obvious how you add those two together. You just add the coefficients, right? Okay, now you need a multiplication. And the multiplication is just the R linear expansion of what the multiplication on the basis elements, namely the group is. I think this is not too crazy. So multiplication is pretty easy. If you take one element, you want to multiply it by another element, then you just do this AG BH, multiply them in the ring, and then what is the extra basis element is just G times H. I think this is a very natural definition. Okay. Why is this an interesting structure? Good question. Thank you, audience. The first thing is actually a combination of Maschke's theorem plus the Wedderburn-Artin theorem It basically says the following: suppose you have a field. So suppose you have F field and then G, and if the characteristic of your field and the order of your G or of your group is co-prime, yeah, well then FG is a semi-simple algebra. Okay, semi-simple. I don't really require the definition of what semi-simple is, but basically, if you have a semi-simple algebra, then Wedderburn-Artin gives you some extra information on what this looks like. Namely, Fg is isomorphic to just a direct sum of matrix rings. Okay, so it's a very, very nice structure. Like this. Okay. And these D's, Di is an F-division algebra. So it doesn't need to be commutative. It can be an actual skew field. Okay, you just take matrix rings over these, you add them together, and that's what Fg looks like. But of course, there's a bit more, right? It's not just arbitrary numbers, arbitrary fields here. Basically, each of these we call simple components, right? So each of those summands is in itself a simple algebra. They have to do with the representation theory of the group G over the field F. Okay, and each component corresponds to an irreducible F representation of the group G. Okay, or in other words, the simple Fg modules, you can all find them in this decomposition as well. This is an equivalent definition. Okay, so really such a group ring, which is also called a group algebra because it has an algebra structure because it's working over a field. It has a lot to do with the representation theory of the group G over this field. Okay, so this is the first motivation on why these group rings were introduced, or well, afterwards what they were, how they were proven to be actually useful, right? So, in a sense, and this is always how I try to sell it to other people, this Fg basically knows about the representation theory of the group G. Yeah, and that's what a lot of modern representation theorists do. They don't necessarily think about the representations as maps, but actually just think about this as rings, okay, and try to understand what this ring looks like. Okay, good. Okay, so that's for the first part about group rings. Now, the second part of the title is free and amalgamated products. Okay, so I will assume everybody knows what Fn is. It's a free group on n generators. I don't think I need to actually define this. But we can generalize such a construction a little bit further. Suppose you have two groups, G and H. And for notation's sake, I will say that G is generated by a certain set I, G, and we add a couple of relations to them. So relations that actually define your group G. And a priori, this can be just like an infinite set of relations. So you literally write every possible relation down if you don't get too tired. And you do the same for H. Okay, so like this. Okay, how can we use these two groups, G and H, to create a new group? Well, I think probably in the first bachelors you see that you can make a direct product of two groups. Okay, those have their merit, but I want to talk about the free product of two groups. And it's denoted in this way. G free product H, and to me this is just the group which is arbitrarily or which is naturally generated by these two G and H. It's IG, and then a direct union with this IH, and here you just take the relations as well. Okay. So what is this group? Basically, you just take any possible words in elements of the group G and of the group H. And of course, there's a natural group structure on this. You just concatenate words. Yeah. But if ever you have two elements of the same group next to each other when you concatenate, you just calculate whatever this is in the group, and then you reduce the work. Okay. This is what's called a free product of the group G and H, and then very easy consequence of this is that Fn is just the free product of a couple of infinite cyclic groups. Okay. Yeah. Do we know maybe some other examples? Well, the free product of two finite cyclic groups of order 2. Yeah, so C2 or Cn is my notation for a cyclic group of order n. So C2 here. So what is this? Okay, just take two elements, right? And the only relations you have is that a squared equals to 1 and b squared equals to 1. And you might recognize this group as the infinite dihedral group, which is actually like an infinite cyclic group being acted upon by a C2. And if you want an explicit, the explicit subgroups here, just take AB as element. This generates something infinite cyclic. And then the element A or the element B, whatever, it acts on this by conjugation, by a, where the element goes to its inverse, namely BA, right? AB times BA becomes 1 because A squared and B squared is 1. Okay, cool. Now I want to go a couple steps further. In such a free product, you're just taking two groups and you're just like smashing them together and creating whatever. Now I want to do this a bit more smartly. Suppose you have two groups, G and H, and I have another group, A, and A is a subgroup of both G and H. So suppose I've got a map I1, or actually an injection, sorry, from A into G. So really a homomorphism, of course. I mean, I want to talk about subgroups here. And an injection into this H. Then instead of just smashing groups G and H together, you can kind of make also such a free product. You just take arbitrary words, but the elements of these images of A instead of G and H, they can be like a double spy. They can both be in the group G and in the group H at the same time. Okay. So how do we do this? Well, let's first write a notation for this. It's G and H amalgamated over the group A. That's what it's called. And it's the following group. So just take G and H, you let them generate the free group, free product of those two groups. And then you put an extra set of relations on them, namely for every element of this group A, you put an extra relation in there saying that I1 of A equals I2 of A. Okay, so it's a very easy definition. For people who prefer this as a quotient group, you can also just take the free product of G and H, and then kill out the normal subgroup generated by I1A, I2A inverse. Okay, it basically means the same. Okay, cool. So this is what's called an amalgamated product. It's a generalization of such a free product of two groups. And it's really like you're gluing the two groups together over like a certain common subgroup that they have. And this construction also has a geometric equivalent to this, or actually this construction has a geometric idea behind this, and in there it's actually like you're gluing two surfaces together. It's really the same wording. Okay? I will not go into detail for this, but there is actually some geometry behind this. Okay, some examples maybe, or some non-trivial examples. Is it better if I do this? And bring this down. Oh, sorry. Yeah, the double angles, for me, this means the normal group generated by all these elements. So it's the normal closure of this group. So you just take it's called the smallest group containing all these elements, which is a normal group of G star H. It's what you would do if you take any group, add some extra relations. Basically, what you're doing is you're just taking the subgroup generated by what you're killing out and take the normal subgroup of this. Okay. A couple of examples. SL2Z, which is, I guess, a very natural group to consider. This you can actually see as an amalgamated product of two cyclic groups. You take a cyclic group of order 4, being a cyclic group of order 6, and you amalgamate them over C2. Maybe some matrices to give you an idea of what this amalgamation is. C2 is generated by -1, 0, 0, -1. This C6 is generated by this element, and then this C4 is generated by this element. Of course, this element squared gives you this one, and this element to the third power also gives this one. That's less easy to see, but you can easily check this. And this is something that you can then moreover prove. Okay, cool. Another one, the third braid group is also an example of an amalgamated product. This is generated by two elements. And you're saying that x squared equals y to the third. This is also called the trefoil knot. Wait, let's first tell you what this looks like as an amalgamated product. It's basically an infinite cyclic group times an infinite cyclic group over an infinite cyclic group. And this shows you a bit what the problem is with the notation, right? It's actually quite similar to if you're taking a semi-direct product of two groups. Just putting this notation does not uniquely define what the group is. Right? You actually really need those injections, but we will always assume that you know what these are. This is also called the trefoil knot group. Why? Because if you know a little bit of group theory, or knot theory, well, yeah, knot theory, as in knot theory, then a very interesting knot to consider is what's called the trefoil knot. It goes something like this. Yeah. And basically this group is, if you just take R3, so normal R3 space, you embed, or you take this knot, or you embed it in the group, you remove it from the space, and then you take the fundamental group, then, yeah.
So the math there are like 1 by 2 and by 3, but that doesn't preserve the unit, so are we?
So, yeah, so the injections, yeah, so it goes to, so first, one of the two injections is times 2, and then the other injection is times 3. Yeah.
Yeah, I was thinking of those 3.
Okay, yeah, no, we're just talking about math groups. Yeah, okay. Right. Okay, so this is amalgamated products. And then there's something that's very closely related to amalgamated products, and those are called H&N extensions. Okay, I'm throwing a lot of definitions at you, but bear with me. So a H&N extension, H&N extension, H&N comes from Higman, Neumann, Neumann, so they're actually names. Suppose you have a group G and then a subgroup A inside of this actual subgroup. And you also have an injection I from A into this group G. It doesn't need to be the natural one. It can be like a deformation. So it can be another isomorphic copy of A inside of G. Okay. Well, then with this information, you can also create a group. You can take, of course, all your elements of the group G. You take a new element T, which is not in the group, so we just take a new symbol. And then now, for all elements of this group A, if you do A conjugated by the element T, this is nothing else than just taking this, this injection on A, right? So you're basically taking the group G, you're embedding it into something larger, where conjugation with this new kind of element on this group A is just taking the map I on it, or taking a homomorphism I on it. Okay? That's what's called an H&N extension. This also proves that if you have such a, well, it's quite easy if you consider it in this way. If you have two isomorphic groups of a larger group G, then you can always embed the larger group G in another group where the two subgroups are conjugated. That's basically what this is. Okay, and that's how H, N, and N actually found this group. They first proved that you could do this abstractly, and then they said, okay, well, this is a very easy group to do this in. Okay. Afterwards, it's easy that this is an example. Okay. Maybe an example. The Lamplighter Group. So the Lamplighter Group is the wreath product of C2 and Z. It has the following definition. It's generated by two elements. You see I like groups generated by two elements. A squared equals 1. It's an element of order 2. And then if you take A to the B to the N, and you take A to the B to the M, then those two have to commute for all N and M in Z. Okay. So this means that if you conjugate B with A, and you take all these, or you take a lot of powers of B, you conjugate all of them with A, that all of those conjugations together, they just commute. So they generate an abelian group. If you think about it this way, it's quite easy to see that this group is an infinite direct product of cyclic groups of order 2 acted upon by a Z, so by an infinite cyclic group. And basically what the action is, it just shifts your whole expression to the right, for example. Okay. Well, then here, if you take this group, so just the left one, to be A and G at the same time, then of course you can embed A in G in a different way by just taking a shift map again. And then of course the H&N extension, I didn't show you what the notation for a H&N extension is, sorry. This group, this H&N extension, it's also written as G and then a star as if you're doing a free product, but you're not writing any group on the left, you're just putting A as index there. This shows, of course, that C2 wreath Z can also just be seen as an amalgamated product of A over A, where the map is the shift. Okay? And then what is this new element T? This is, of course, just this Z that you're adding to. All right. Yeah. Okay, I'm running out of space, so let's start some cleanup. Okay, so we have now defined two very relevant groups, H&N extensions and amalgamated products. And those two groups appear in geometric group theory because they are basically the basis of what is called Bass-Serre theory. Okay? So Bass-Serre theory within geometric group theory basically tells you what a group looks like if you know how it acts on a tree. So you get a group, you get a tree, you find an action of the group G on the tree. Well, then from this information, you can basically construct the group or reconstruct the group G via taking amalgamated products and H&N extensions. Okay, this is the whole big idea of Bass-Serre theory. Okay, so that's why I said that those groups really have a geometric group theory flavor. And there's one property that both groups share that will be basically the most important property that I consider them to have. And it's about finite subgroups. So suppose you have a group G and an amalgamated product over H, and you have a finite group G inside of there. Well, then what you know is that for free, you get that G is actually in a conjugation of G or H. So this group is an immensely large group, but if you find any finite group inside of it, then you know it's actually just conjugated to a subgroup of the group G or of the group H here. Yeah. And the same goes for a H&N extension. If you have a large group G amalgamated over a subgroup A, you take a finite group G inside of it, well, then you know that G is conjugated in the smaller group G. All right. So finite subgroups of these kind of groups, you can basically recognize them in smaller groups. Because of course, up to conjugation, so you know that up to isomorphism, they are in the smaller groups. Okay? Yes, G. G is conjugated in G. It basically means that G, there exists an element of the group, so of this large amalgamation, for which G actually is a subgroup of G to the X. So G to the X considered as a subgroup of this amalgamated product. Yeah. You can find your small g inside of there somewhere. And this is not true for any group, for any subgroup of this. Right? Because, I mean, it's quite easy to see that the whole group is not in just this G conjugated, because it's much larger than just the group G itself. Because you have this extra element T there. Okay. So this really is a special thing appearing here. And in what's going to follow, so when I return back to group rings, you will also notice that I will talk almost solely about finite subgroups within group rings. And this is going to be, in the end, the link to amalgamated products and H&N extensions. Okay? And I hope I have time to actually show you what the link is. Let's see. Shit. Okay, I will have to be a little bit quicker than this. I'll just talk about one conjecture in group rings then. I will talk about the isomorphism problem. So think back on group rings. You basically know that group rings kind of say what the representation theory of this group G is over the field or over the ring R that you're talking about. So a natural question could be, thus, if you have an isomorphism between RG and RH for two finite groups, does this imply that your group G and your group H are isomorphic as groups? So here's an isomorphism as rings. Does this imply this? Informally, you could say, does the representation theory of if you have a group G and you know its representation theory over a certain ring, does this then uniquely define the group G? I'm swiping a tremendous amount of theory under the rug by saying this, but that's the idea. Okay. Let's start with R commutative. Okay, then it's quite easy to see that RG is commutative if and only if the group G is commutative. Okay, so at least this group ring remembers a couple of things of your group, namely, for example, the fact that it's commutative. Also, if you have RG isomorphic to RH, then at least those groups have the same order. And this is just from the fact that its additive structure is a free R module. Okay, so you can construct the elements of the basis elements of this. Okay. Their basis theory actually works within modules if you take just free modules. Okay, so this is some easy stuff where you think, okay, this might start to work. You might actually get there because this you can, if you just write this down, these are the next two things you write down. Okay, but then unfortunately, in what year? In the 70s, Dade actually tells you that it's not as easy. So Dade in the 70s, he showed there are non-isomorphic groups G and H, for which Fg is isomorphic to Fh for every field F. This is crazy. I mean, this is highly non-trivial for every field F. A couple of facts on these groups G and H. They are both of order p to the 5, q to the 6. So we actually found a lot of examples, and all of them were of the order p to the 5, q to the 6. So they involve 2 primes. And the groups are both metabelian. Metabelian is another word for abelian by abelian. So you have an abelian subgroup, and if you take an abelian normal subgroup, and if you take the quotient, you get an abelian group again. Okay, that's what metabelian means. Okay, so this was pretty strange that at least this, the isomorphism problem, is not true when you just consider fields. Okay. And groups which allow 2 primes. Okay, from this point on, basically the research or this problem was reduced to 2 subproblems. First, the modular isomorphism problem. So basically, can a counterexample exist among P groups? Okay, and of course, sorry, I'm saying of course, but this is not of course, but I'm assuming my ring to be a field, right? So can this example by Dade be generalized to actually 2 P groups? Okay. So here you're allowing 2 primes. Can this be done? And it's only in the last year, so in 21, that it's actually shown that there are 2 P groups that have 2 different P groups that have isomorphic group algebras over every field. Okay. So here the answer is yes. So there is a counterexample among P groups, and this is done by Garcia, Lucas, Margolis, and Del Rio. And Margolis is Leo Margolis, and he was at the VUB at that time. So pretty impressive. He's a pretty good guy on finding counterexamples within group rings. I will skip over a part where I actually show a couple of extra counterexamples that he found to conjectures that were already standing for quite some time. Yeah. Because this one, this first is stated in the 40s. Yeah, so it's like at least 80 years old. Okay. All right. Okay, so this way of thinking about it is a dead end. Can we do something else? Well, here we're talking about fields. Maybe we can actually prove this if we just say, what about if we just take rings, yeah? Or arbitrary rings? Okay, can we find a ring for which this actually holds? And then there, the most natural case is Z. So that's what they call the integral isomorphism problem. Does ZG isomorphic to ZH imply that G is isomorphic to H? Question mark. The motivation is here that Z is kind of a base case for what a ring is. It has a 0, it has a 1. You can add, you can multiply, and that's basically it. At least if we're thinking about characteristic 0, right? But if ZG is isomorphic to ZH, then by taking the tensor product with any ring R over this Z, you can automatically get this. Yeah, so it really is like a very base case of this isomorphism problem. Okay. So if you're able to find a counterexample for this, then it should be true for this integer, for the integral. Okay. Cool. So this idea was done, I think, in the 60s. No, also in the 40s. Sorry, this was actually one of the first remarks that who was it? I think it was Higman made when he first made that statement. That if you find a counterexample to this, then you should be able to find this over the integers. And the answer to this is known, by the way. I'm keeping you in suspense until this is clean. There is a counterexample. The counterexample was found by Hertwig, Martin Hertwig, in 2001. Well, it was actually found before, but he published it in 2001. And apparently, he published this while there was actually a conference on group rings happening. And of course, you can imagine that the rest of the conference, there was only talk about this example, and there was no more listening to the rest of the talks. Must have been fun being there. Must not have been fun giving a talk there. Yeah. Okay. Okay, so I'm being very negative right now, yeah? So I'm just giving this this certain conjecture and then saying, no, there's counterexamples to like every possible way of thinking about this. But nonetheless, this statement was non-trivial because there's many positive results on this. So for example, if you have a group G there that's abelian or nilpotent, then the integral isomorphism problem actually does hold. Yeah? And even for metabelian groups, it also holds. So this counterexample that Dade found is not a counterexample to the integral isomorphism problem. So it really is more interesting than just people not being smart enough and seeing an obvious case. Okay. All right. So if you want to think of these kind of problems, what should you consider about the group or about the group ring RH or ZH or ZG? Yeah. Yeah. So I have to say that one I don't know, but it's So it's a P group, so it's nilpotent. Okay, truth bomb there. It was shown to hold, I think, for P groups which are of nilpotency class up to 3, and the counterexample is 1 higher. So it's like it's a nilpotent group of class 4. So it was like the smallest possible nilpotency class there could be a counterexample. That one they found, and then this one, the order here I do know because it's funny. It's of order 2 to the 21 times 79 to the 28. See, it's a funny number. I don't know why, but it's a funny number. Yeah. Well, okay. There, of course, the counterexample should exist of 2 groups, but they have the same order. So this is the order that both of those groups have, and it's a metabelian. No, it's not a. It's not a metabelian group. No, it is a solvable group. That's also interesting. Okay. Right. Some extra truths. There is a very easy ring morphism from ZG to Z. It's just forgetting about the group G. So if you take AGG, you just map it to the sum of all the AGs. It's a ring morphism. All right, pretty cool. If you have a ring morphism, then you know that you can restrict this to a group morphism between the invertible elements. So if in UZG you take, if in ZG you take UZG, which is just the subgroup of all invertible elements, yeah, then there is also a map to what are the units, what are the invertible elements in Z. It's not a lot. It's plus minus 1, okay. And it's also quite easy to see that the kernel of epsilon, which we denote by V of ZG, that then UZG is just plus minus VZG as groups, because it's just this minus 1. This minus 1 is going to be central. You can work this out a little bit, but basically the group, all the unit group, you can, if you want to describe this one, then you can just describe all the elements which are in the kernel here, and they're called the units of augmentation 1, because this is an augmentation map. Just a name for something like this is the general construction in algebras, and it's the ones with augmentation 1. Okay. And I prefer group theory to ring theory, but I've almost always been talking about rings. So why am I doing this? Well, you can pretty easily show that ZG is isomorphic to ZH if and only if UZG is isomorphic to UZH. This is extremely remarkable. Normally, 2 rings, I mean, from 2 rings, you cannot conclude that they are isomorphic if you just know that they're elements that are invertible are isomorphic. But if you know that they actually are group rings, then you can actually say this. Okay, and then of course these 2. You can just actually forget about the ones that do not have augmentation 1. Okay. So V of ZG. Those are all the invertible elements. It's a kernel of this map as a homomorphism, of groups. Yeah. I don't know. No, I don't know. If anybody has an answer to this, it can be very interesting. But yeah, I don't know. Sorry. Okay. Where was I going with this? Yeah. Okay, so maybe some other very obvious things. The group G itself, it can be embedded in ZG. Of course, it's just these basis elements. And all these elements still remain invertible. I guess that's quite obvious. So this is a subgroup of UZG. or even more general RG. If this ring R has invertible elements, then they also remain invertible in this. This is all very, very trivial if you just think about this a little bit longer than a minute. So it's quite easy to see that if you take any invertible element of the ring R and you multiply this by any element of the group G, then this whole set or this whole subgroup will be a subgroup of all the invertible elements. This is what they call the trivial elements because they're trivially. I've used nothing of the structure of the group G or of the ring R. Okay, and so this is also where this plus minus comes from. Yeah, it's the only elements that are invertible within Z, and it is really those elements that you're using here to make this product. Okay. All right. Keeping this isomorphism problem in mind, if you have ZG isomorphic to ZH, then those groups are isomorphic. So you know basically that this H is a subgroup of UZG somewhere. So this isomorphism problem really is about finding finite subgroups within UZG. And if you can find a subgroup which has the same order than G, then you've basically found an isomorphism between those two things. This is not a triviality, but it's actually true. So if within UZG you can find a finite subgroup which has the same order as G, then this becomes an isomorphism. This is again highly non-trivial, but this actually works. So the question here becomes finding finite subgroups within this large thing. And now I want to harken back to the end of my first part, where I said that if you have amalgamated products or if you have H and N extensions, then you can kind of find where the finite subgroups are. You basically split it up into smaller problems, smaller groups. Okay. So that's the link between the two. Okay. So how are we actually going to link this in a bit of a stronger way? That's my part 2, which will last 10 minutes. It's studying UZG or VZG, which is basically the same. Yeah. So in the last, let's say, 30 to 40 years, there's basically been 2 ways of trying to studying these groups. First of all is what group theoretical properties do they have? It's a very easy way of studying a group. Is it abelian? Is it a free by free group? Is it whatever you want? Okay. And another way of trying to study this is trying to find concrete elements that are in here. So I said here that these are trivial elements living inside of your group ring. But the question, a very obvious question to ask is, when is this an equality? And actually the answer is it's very rarely an equality. There will be a lot more invertible elements than just these obvious ones. And basically, if in your group G, you have an element of order not a divisor of 4 or a divisor of 6, then you will already have something that's much larger. Again, this is also not a triviality, but it's you can actually pretty easily construct one of these if you know where to look. All right. So let's first take the part where we're trying to consider what other invertible elements are there. Question mark. And then I will just write a couple down that have been known for many, many years. First of all, if you think of Z adjoint zeta, and zeta is an nth root of unity within the complex numbers, for example, you take like its ring of integers. Yeah. Then in here you can find cyclotomic units. And cyclotomic units is basically something of the form like this, and it is z to the k minus 1 divided by z minus 1, and it's invertible within this ring. So of course it's invertible within, well, if k is not equal to the order of zeta, then this is invertible within the complexes, right? But it's actually even invertible within this subring. Okay. This was the inspiration of what they call bus cyclic units. And they're of the following form. Take an element G of your finite group G. Well, then you can make 1 plus 1 plus G plus, whoops, plus G to the K minus 1. But there has to be more. You can take powers of this as well, but there has to be even more than this. And you can, it's actually quite easy to see, because if you take the augmentation of this, so you just take the sum of all the coefficients, then it's going to be k to the m, and k to the m is generally not invertible in Z. Yeah, so that's a problem. So what you do is you do 1 minus k to the m divided by n times G tilde. And G tilde, it's an element that's used a lot in group rings. It's just the sum of the powers of G. Okay. It's a bit crazy that just adding this works, because it's like it's an obvious extra, let's say, number you have to add to make sure that if you take now the sum of all the coefficients, that it becomes 1. But apparently, with this definition, you actually get a unit. And the thing is, this is a unit of infinite order. Okay, so yeah, it has infinite order. And from the, you can make this exactly when the order, or sorry, it's not trivial, or it has infinite order, sorry, if this order of G is not a divisor of 4 or 6. And that's why I said that from the moment you have such kind of elements, you can make infinite, you can make this unit group to be infinite because you have an element of infinite order. No, you choose k. You can choose arbitrary, again, not being not 0 modulo the order of G. It's quite similar to what you do here. K cannot just be a multiple of the order of G. And then m, okay, so m is also chosen arbitrarily. And this m is basically just the mth power of, if you would just take m equal to 1. If you then would calculate this out, then this is just the mth power. But then the inverse of this, there you need to do some more maths on to find what kind of, what the actually inverse is. Okay. Sorry, the n, yeah, I just, without thinking, wrote down what I wrote here. I should not do this. This n is actually the order of G. Sorry. Yeah. Thanks. Okay. Cool. This is one example. There are many more. I will use a new piece of the blackboard. Well, I would say there are many more. There are actually not a lot of extra that we know. However, I'm going to give you at least one extra example. You take two elements of your group G, and now you make the following elements. So I again write H tilde, it's just the sum of the order of sorry, all powers of H. This is invertible, or even in V's of G. And what is the inverse? This. And what is its powers? So if you know a bit of of linear algebra, if you work with linear groups quite often. This looks quite a lot like I was going to say nilpotent unit, it's not a unipotent unit. It's like 1 plus something, and if you take powers, it's just doing m times this extra bit here. Okay? And this is also really where the inspiration of this comes from. And the link is even better because you know that group rings and representation theory are linked because of these components. Well, such kind of elements will also map to unipotent invertible elements in all of these components. Okay, so that's also pretty cool. Now, of course, this can be trivial. If you work this out, it's possible that this becomes 0. Okay. Now, when does this not become 0? For example, when h to the g is not an element of the group generated by h. If this is not, if this is true, then this is actually not equal to 0. This is also something that you can do, that you can quite easily show. Okay. With this, and with this link with unipotent invertible elements, you might also think that these are elements of infinite order, and yes, indeed, they are. They are actually elements of infinite order again. Cool, so we have now 2 examples of units which are of infinite order. And these have been around for pretty long. I think they were first invented in like the 80s and 90s. Okay. But up until 2015, there was no example of such a kind of generic construction that gives you a unit which is not trivial, so it's not inside of the group G, and that has finite order. Okay. It was only in 2015 that Bovdi came up with the following construction. And you might be very surprised that it took so long. So instead of writing a 1 there, you just write the group element H there. Well, in 2015, Bovdi was the first to actually publish that this is a unit. So it is invertible, and it will actually have the same order as the element H. So that was the first kind of new way of finding elements of infinite order. And here, this is again not 0 if and only if that holds, right? So it actually gives you new units. Okay, I will take 1 extra minute. That's all. All right. So in this paper, Bovdi introduced them, and then this was at the beginning of my PhD. We were actually able to show that these kind of elements, if you take this, and then if you also take, this element, yeah, that this gives you a free product of cyclic groups. At least this is what I had hoped that would be proven in my PhD thesis. I was able to show this for a lot of different groups. But the proof basically goes in finding a good representation where these both map to matrices where you can actually see that that should be isomorphic. The group generated by those two should be isomorphic to such a free product. It also has to do with these unipotent units there. But because we're trying to, or the proof goes via trying to find a good representation, it just doesn't work for all the groups because an arbitrary group has a very difficult representation theory behind it. But at the moment, so, and this is joint work with Geoffrey Janssens, we're actually trying to take this construction and blow it open and basically try and find the most arbitrary version of a free product, namely an amalgamated product, and see whether you can actually find this. So if you have H and K, both subgroups of G, can you then find free products of H and K or actually an amalgamated product? And we think that the amalgamation should be over the intersection between those two within UZG. Yeah. And the way we do this is by basically trying to find such groups within algebraic linear groups. So we're really using, we're actually really using the representation theory again, but now we've gone about it in a little bit smarter way than what I was just able to do in my PhD. And we're really just translating into, can we find such subgroups in algebraic linear groups? So basically our next paper, it should be finished on Tuesday. There, it's really just about trying to find such amalgamated decompositions within algebraic groups. And yeah, there you have a lot of fun things going on, right? You can do like a ping pong lemma if you want to get like free products, if you know what a ping pong lemma is. We found a way of using ping pong to create amalgamated products, and then we were inspired by these elements and then these unipotent elements to construct such groups. Okay, I will stop here. Thank you.